one.
So, hello everyone, and thank you for joining today's PLC2 webinar. It's the PoC-Library Memory Implementations. My name is Anna Krassin, and I'm your host today. So this is the fourth webinar of our series where we are focusing on the open source and free component PoC-Library. And if you missed the other parts before, this is no problem. You can all have a look on our website. There you can all see our on-demand webinars and on our YouTube channel. At the end of the webinar, there you can have a QR code by scanning directly to our website to see all the webinars you missed. So before we start with the webinar itself and focusing on the memory abstraction layer in the PoC-Library, I want to talk about a few general things. This webinar will be about 1 hour, including our Q&A with your questions. So please ask questions, then our expert can answer them at the end. So this also is a recorded session, so you as an attendee will get automatically an email afterwards with a direct link to the recording, so you are able to have a look in your own pace at the whole webinar afterwards. Then we focus on the go-to panel itself. It may look a bit different than yours, but we are focusing just on 2 sections. This is the question section where you can ask questions, but we are using also an extra plug-in called Slido. I will show you after this slide a QR code, and there you can scan the code and you will automatically come to a question platform. And really important for you is here you don't have to register or something. There's no account required. Just scan the code and you will come automatically to this platform, and then you can ask your questions and you can see other questions from the other attendees and can also vote for them. If you think there are another questions, they are also important for you. Then the second section here, there you can see, is the handout section. There is our training calendar for 2026. There you can see all of our training courses, from 1-day courses to 5-day courses, with all the dates and more informations about the agenda and the topics related. So please have a look on that. So then I have to have a look here. So this is the QR code you should see.
Oh. Something wrong with the plugin. No, we have it here again.
Okay, then here you can see the QR code or the hash. So please use that to register on the to come to the question platform. So I will now talk more about our speaker today, as you can scan the code. So today, when maybe you know him already from the other webinars from the PoC-Library, is my colleague Patrick Lehmann. So he's a long-time trainer for PLC2 for several training courses and also the head of system engineering. And he is one of the developer and maintainer of the PoC-Library. So this is a huge part for the PoC-Library and our series here. And he has a passion for the open source and has active roles in several projects as the VHDL project, the PoC-Library, or the IEEE P1076 working group, where he plays an active role too. So thank you, Patrick, for being here, and I will now hand over to you.
Yep, thank you, Anna, for your introduction. So let me go back from our workaround showing this slide with the QR code. A short note on PLC2. You mentioned already our training calendar for the next year. That's now available. either as a download here from GoToTraining or GoToWebinar, or also on our website. So PLC2 is originally coming from the training section, doing trainings explicitly and exclusively with former Xilinx, nowadays AMD. We are an authorized training provider. We are a coaching service provider. So when you need access to the official training material, consultancy work, whatever is needed to help you in your projects, maybe to reach your deadlines, whatever you have, timing problems, you can reach out to us, or in case you start a new project, we also have training classes offering you transitions to new technology, updates to MP-SOCs, versions, whatever it is. The second part, when it comes then to some bigger projects, we also have development services directly. We are also an AMD embedded partner, a premier partner. So when it's bigger things where we can help out or should help out, or you have not enough manpower expertise, we can also help you. And finally, PLC2 also has some products. So we have a few IP cores, we have a data logging solution that's also all available on our website. So these are the three main foundations of the PLC2 company. So let's go on now with our webinar itself, the PoC-Library and memory implementations. In the last webinar, we asked for certain preferences. What do you want to see next? And we decided then, based also on your feedback from the question and answers in Slido, what we should pick. So we picked the memory implementations. Before I go there into all the details and implementation work, I want to give some information background for the people who have maybe not attended previous sessions. They are all available on our website. They are also available on YouTube, so you find also the recordings there if you want to see them. I want to point out that the PoC-Library is available on github.com/vhdl/PoC. That's a forked version from the original PoC that is maintained. The old one was from the share of VLSI design at TU Dresden. This is not maintained anymore. So we have now a new fork of this PoC-Library, which is maintained by me and a few colleagues, and we get contributions from different people. Some, of course, in the company of PLC2, because we are using it also internally with our projects and consultancy work, but also external contributions. There's also documentation available at vhdl.github.io/PoC. And in case you use the star symbol in GitHub to give us feedback if you like the library, or if you want to have use this library in your bookmarks, we are happy if you add another star and put this into your bookmark. Just take care that you do this on the right place, which is now the new location, vhdl/PoC. In case you want to get updates on new releases, there's also a bell symbol. That's a little bit like YouTube. You can also select here, don't get every notification, just releases. So in case we have a new major release, you get automatically an email. That's up to you what kind of notifications you want to set up. We also pulled a tiny comparison, how the PoC-Library is behaving, especially compared to the old library. That's the yellow line. So we see there's certain feedback, maybe because of this webinar series, maybe because of other presentations we had. So we see that the PoC-Library is now revived somehow, and we hope to continue this traction. Speaking about what we promised last time and about contributions, there is a user called G. Martina on GitHub who provided lots of translated test cases. So he translated old test cases into the new OCVM style, integrating this into the framework we set up on the PoC-Library. And we have now a total of 27 test cases running automatically on the server. And so far, there were no findings. It was just a pure translation step from old style to new style. I think that's a good result. And we will contribute further test cases, and maybe this user is also, or other users are also contributing to test cases to show what the test coverage is. Last time we also got feedback on our documentation itself, and some pages were broken, especially after we released the register and Git version register. So I want to point out here that we are working also lots on the documentation. that there will be a Linux kernel driver with debugfs functionality for the Git version register, allowing you to mock certain data fields inside. And there's also an ongoing discussion for new features itself for this register. So people are interested and give us feedback. And just to show you some documentation here, this is the register description of the Git version register. This is now online. And in case you have done the PDF variant of the slide, it's also clickable. Oh, camera off. Yeah, sorry. For upcoming releases, we made a plan what is next. This will be an AXI Lite set of updates, a high resolution clock, an OCRAM adapter, so many adapters to BlockRAM, a UART, and an adapter to the DRP port for Xilinx devices. This is what we sketched together as a next release plan. And we also had a discussion what might be a good topic for the upcoming FPGA conference in 2026. And we are talking internally to release the AXI4 multiplexer and demultiplexer structures, that we get then a full set of AXI devices, just to give you an update what might be coming next. Okay, so then let's go to our presentation here, our webinar about part 4. As I said, the previous 3 webinars are available online and they are recorded. And today we want to focus on-chip memory, on FPGAs, FIFO implementations we can derive from the memory, and AXI4 FIFOs derived from these FIFOs. So I try to build up a certain chain of reuse in here. Okay, on-chip memory. First, let us talk about the different memory technologies that are available on FPGAs. Of course, we have single flip-flops, which is a 1-bit memory that we can use, maybe not ideal for bigger memory implementations. Then we have lookup tables that we can use as RAMs. A typically implementation might be a lookup table with 6 inputs. This gives us 64 bits of RAM. If we combine 4 lookup tables in one CLB together, we get 256 bits of RAM. Another option is using shift registers like SIL32. This would give us 32 bits of shift memory. We will later see an optimized version for FIFO. Then next level would be BlockRAMs, an even denser memory implementation. Depending on the vendors, they have different names and sizes like M9K, M10K, and so on. In the AMD Xilinx world, they are called BlockRAM with 36 kilobits and UltraRAM with 288 kilobits. And in Lattice, they have the embedded BlockRAM with 18 kilobits. Then another memory technique that is available is external memory. It's maybe not in the scope of this presentation. Just for completeness, we can have static and dynamic external RAMs like QDR SRAMs or DDR SDRAMs. This is possible. Maybe in a later state, we can give you a presentation about a memory controller like a FIFO that is using external memory. So in case you need very big FIFOs not fitting into the BlockRAMs, we also have a solution for it. This is currently an internal IP to PLC2, and maybe in a year or 2 we can discuss about this technique. Just doing a rough estimation here is, let's take a RAM implementation for 256 bytes that we need. So it's 1 byte is 8 bits times 256 words. We can implement this in 8 CLBs. It's very dense implementation. We don't need to jump directly to BlockRAMs. Some memories to a certain size are implementable in lookup table memory without jumping to BlockRAMs and wasting their memory space. So always keep in mind what your architecture underneath is supporting. So maybe do not set up a memory of 300 words. Maybe you can fit it into 256 to get the benefits of a CLB and not jumping directly to the next bigger stage. Comparing the different features of memory, I tried to make columns here for our 4 technologies and then write down what features are available. So all memories can be initialized. This depends also a little bit on the vendor itself. What is available in Xilinx devices, for example, you can initialize flip-flops either to zeros or to ones. Other vendors are limited just init values to 0 or reset values. When it comes to resetting certain memories, flip-flops, of course, we can reset. With bigger memories, there's no reset available. Just imagine the number of current and power you need to clear a complete BlockRAM at once. If you would trigger this whole BlockRAM would just burn inside of the ASIC. So it's a power problem, a heat problem, and especially if you have multiple BlockRAMs together, like 16 connected into one memory, it would be just a too big power draw inside the FPGA. So no resetting available. All these memories support the implementation of dual port memory. There are also ways to implement more than 2 ports if needed. This is usually done by replicating the memory and saving a word multiple times into memories. All these memories are capable of cross-clock except for the LUTRAM. So that's one optimization to get bigger memories on the UltraScale Plus devices. They sacrifice for the second clock input. We have byte enables available with BlockRAM and LRAM, and we can emulate this based on the VHDL code with single flip-flops and lookup table memory. Writing is always synchronous into the memory, and the first 2 variants have asynchronous reading of data. Summarizing all this means we need to avoid memory implementations made of single flip-flops because it's just too much device utilization if everything is done by a single flip-flop. This also means do not connect any reset to your memories, to your RAMs itself. Otherwise, it's forcing synthesis to use single flip-flops. And with LRAMs, we cannot use them for cross-clock FIFOs. That's one limitation. And the synchronous write and synchronous read operation requires 2 clock cycles. So if you want to write generic VHDL code that's inferring BlockRAM and LRAM, or has a possibility to switch between all these different techniques, we need to write it down with two clock statements in one process in VHDL. For the PoC-RAM implementations, what are the FIFOs, features that we have here? The memory is independent in area, so you specify the number of bits per word times number of words you want to have. So we are specifying in area as your memory, and we can implement any size. This also means if you go beyond a power of 2 number, then usually synthesis in the background will automatically use the parity bits with the provided instances inside of your device. We can have any number of words. Usually it's rounding up to a power of 2 number because this is what the underlying structure is providing. And we are not bound to any device primitives. So compared to using directly a RAM B36, which is exactly 36 kilobits, we describe just a size, and then synthesis will figure out what is needed, or combining multiple primitives together. So as I mentioned, the RAM B36, the calculation here for 36 kilobits is done by taking 32 data bits plus 4 parity bits times 1024 words, and this gives you 36 kilobits. So usually it means you can have 1024 32-bit integer variables or values, whatever you have in one memory block. As I said, there's a synchronous write and read operation, and this means synthesis can decide for the RAM type itself. And if a LUTRAM is selected by synthesis, which means that there is a synchronous write operation but asynchronous read operation, then synthesis automatically will add another flip-flop on the output side to create the synchronous read operation. Then again, we have 2 cycles delay in the RAM implementation. We have a selectable RAM style with all our implementations. So usually it's set also by default to automatic. and you as a user can override it to a different style if you like. We can initialize our OCRAMs with files, and for AMD Xilinx devices, this means there's a hex file format, one line of hex encoded characters or string per word. And for Altera devices, there's a MEF format, that's the memory initialization file format. This can be read by Altera devices. This means, as I said, we can initialize RAM content itself. We can also use this for static ROMs to initialize them. And the VHDL description is usually generic, except for some parts for Altera due to the file I/O. So we are using here primitives that we can hand over the file name to an alt-synchram module inside, which is then capable of reading MEF files. Inside of our PoC library, we have different namespaces. The general namespace is mem, like memories. In here, we have a memory package implementing certain types and helper functions. We have here the data structure for our Git version register with some data types again. Then we have underneath mem another subdirectory called OCRAM. And here we have four important implementations. OCRAM SP is a single port, then we have SDP for simple dual port, then there is an enhanced simple dual port variant and a true dual port variant. On the right hand side, I made some drawings for you. So in a single port, you have one clock, one write and one read interface. It's operating together with a combined address. A simple dual port, that's usually what's used with FIFOs. You're writing on one side with one clock and you're reading on another side with another clock. This is typical for FIFOs or cross-clock FIFOs. Of course, the second clock can always be the same as the first one, but it's capable of having here dual clock implementation. And then the third one is a true dual port RAM, where you can independently read and write on both ports. Of course, you need to make sure that you don't have an address collision. Otherwise, a bit undefined what happens. Then there's another namespace called OCROM. So these are ROM implementations with a single port or with dual port, so two ports usually. This is then used in combination with the init file. So if you have a big set of constants you need, this is one way to load them into your design. And third subdirectory is mem.lut for lookup tables. So we have here an implementation of a sine wave, and you can specify how many words and what accuracy you want to have. And depending on this, it's generating then a ROM inside. Okay, so based on these primitive implementations of memories, we can now compose FIFOs. And as the idea is of PoC, and we call this a PoC-Library because they are IP cores dependent on other IP cores or modules inside of the library itself. It's not just a collection of IP cores. Of course, our FIFOs are dependent on the OCRAM. This gives us vendor-independent implementations. We are size independent. We are not bound to any primitives in the device, and we can also use the features of OCRAM, like selecting the RAM style. That's quite nice that it's built on top of it. This means the synthesizer, as I said, can decide on the memory technology itself, and the user can override it. So what might be a use case? Let's assume you have an UltraScale Plus device with lots of UltraRAM available. Usually synthesis will decide for BlockRAM and use all your BlockRAM, and you have a big video line buffer, and then you use the RAM style, you override it and force it for the video line buffer to use UltraRAMs. So you use these big RAMs together as a chain and combination for your video line buffer. You free up lots of BlockRAM resources that you can use for other purposes, maybe for an ELA, for debugging resources, or whatever you need. That's also how the idea inspired my colleague to implement this feature. If FIFO itself has a simple put and got interface. So put and full is on the writer side. So you put data into the FIFO, you get feedback if a FIFO is full. And on the reading side, you have an empty signal and you have a GOT handshake. This is then, yeah, the basic handshake of a FIFO. Some other implementations use different names like valid instead of empty. That's just the inverted one. All is possible. In addition, our FIFOs are providing a fill state. The fill state is on the consumer side, and it gives you a minimum guaranteed fill level. Usually, we set up the fill state with a number of bits. So in case you select 2 bits, you get like a quarter, half, 3/4 of full as an indication. And on the producer side, so the writing side, you have an empty state, which is a minimum guaranteed clearance level. So in case your FIFO gives you a combination in, if I calculate this and now as an integer of 1, so you have then a quarter of clearance still left, which means you can write a quarter of the length of the FIFO still into it without getting any full indication. So we always have these guaranteed fill or clearance levels with our FIFOs. If you set the number of bits to the logarithm of 2 of the whole FIFO length, then you get a word by word fill level, but usually this is not needed in designs. So indications like in quarters or eighths is already enough for most use cases. And this saves then resources in the internal implementation. So let's have a look at the interface of our FIFO. I'm taking here the example of FIFO CC GOT. The CC stands for common clock, so it's a implementation just with a single clock on or running on both sides, producer and consumer side with the same clock interface. We specify the number of bits, data bits. We specify the minimum depth. As I said, it's usually rounding up to a power of 2 number. That's the number of words. Here we see the RAM style, how you can override it with a different style in case you want to go to BlockRAM, LUTRAM, whatever you like to have. We can enable certain optimizations like data registers, state registers, output registers. This takes a few more resources for the internal logic, but it can improve the overall frequency you can reach. Then, as mentioned before, for empty states and fill states, we have the E state write side bits and the full state read side bits. Currently, it's deactivated. If the user specifies a number of bits, then the port interface is activated and is providing to you the empty state and fill state. For the writing side, as said before, we have, of course, a clock and reset. We have the put signal to put data into the FIFO. We have DIN for data in and a full indication if it's full. And on the consuming side, we have a valid and data out, and then we have a GOT signal to indicate that the consumer consumed the data and the next data should be presented on the output. So this is then the implementation of a first word false through mechanism in here, and this can allows you to have very good and performant implementations together. For example, with state machines, they can always sneak preview into the data that's available as a topmost element in your FIFO. Having a look at all variants of PoC FIFOs, we have FIFO CC GOT. That's a common clock, as that's our standard FIFO with a GOT interface. In the past, the PoC-Library had another interface with GET implementation or GET behavior. This was removed already some years ago. Nowadays, we have everything with GOT interface. Maybe that's one of our tasks for the version 3.0 of the PoC-Library, to have another cleanup round and get rid of the GOT interface name in here, because it's just redundant in all FIFOs. We can talk about this. Our cross clock FIFO, this is the IC GOT for independent clock. For the common clock FIFO, we have 2 special variants with temp GOT and temp put interface. So temp GOT means you have a temporary extraction of data, so you temporarily take it out. And in case you have a transmission error, you can reset the readout pointer to the old position. and then you can read out again from this old position. So actually, this is implementing a retransmission buffer with a commit and rollback feature. When we have a retransmission buffer that's on the sending side, we need a similar implementation on the receiving side. So we have the temp put FIFO with a temporary insertion feature. So this is implementing our receive buffer. Usually this is used in combination with, let's say, CRC checks. If your CRC check is okay, you acknowledge the internal data with a commit signal, and then the consuming side can see the data. If the CRC was invalid, the write pointer is reset. You can reuse the space and receive another frame of data, let's say an Ethernet transmission. A special implementation of FIFOs is the FIFO shift. This is using shift registers. This was implemented as an optimization technique on AMD devices, providing SRL32 shift registers. And the benefit here is we can avoid one counter in the implementation. Usually you have one read and one write pointer, which is then a pointer then in the background a counter implementation. So we can avoid one counter just by shifting and then specifying the readout counter. And another special variant is FIFO stage with a common clock. This is a two-stage FIFO. Actually, that's the smallest FIFO you can implement. And this is used for decoupling critical paths. So we are decoupling valid and empty signals, or valid and other handshake signals, however you want to name them in your design. And this is one of the key foundations if you want to have pipelining in AXI networks, AXI Lite, AXI-Stream, AXI-Full. You need such a stage. A normal register stage is not enough. You could pipeline the valid signal that is going forward with your data, but you cannot pipeline the ready signal that is coming reverse from your subordinate. So to break the critical path on the reverse line, you need to have a two-stage FIFO implementation, and this is done by FIFO stage. I'll also summarize the interfaces here in these tiny block diagram drawings. So having a look at our FIFO IC GOT, it's a very similar interface. Certain features are not available in here, like implementing this with shift registers. So this is gone from the generic list, but otherwise the interface is very similar. It's only adding here a clock and reset on the reading interface side because it's cross clock or independent clocks between writing and reading side. Okay. With these foundations now in FIFOs, we can go one level up into AXI FIFOs. And here again, it's based now on PoC-FIFO namespace implementations. We are inheriting all features from before, actually inheriting this from OCRAM. We are vendor independent, size independent, and we have a selectable RAM style with our implementations. And as before, synthesizer can decide and user can override certain features. And we have done these implementations for all kinds of AXI4 interfaces, so AXI4 full, light, and stream. Taking this together into a table for an overview, and you find this under PoC.bus, or as directories then inside of the bus subdirectory in our source directory. You find an AXI4 FIFO and AXI4 FIFO CDC, similar the combination AXI4 Lite FIFO and AXI Lite FIFO CDC, and of course again the same variant combination Stream FIFO and Stream FIFO CDC. And for Stream we also provide an AXI or a stage variant to decouple, as I said, the critical path and AXI-Stream interfacing. It's on our list to integrate this variant into the normal FIFO here just by setting the number of elements or that are inside to 2. So we can combine it in the next releases somewhere into FIFO. Having a look at the interface itself, in our last webinars, we showed and introduced our AXI data types and infrastructure, how it's made. We are using 2 record data types one for manager to subordinate, and one from subordinate to manager. So one record forward, one record backward for all AXI signals. And we can therefore limit then the number of ports in our port lists here just to 2 signals. Then, of course, we need the clock and the reset signal in here as system clocks. In case what I'm showing here is a CDC variant, so we also need the clock and reset from the output port side, from the consumer side, and this is all what we need to connect. We also have internal discussions how we can go forward into the direction of VHDL 2019, providing this as real interfaces with mode views. Then we can reduce it completely to 1 input and 1 output port. What you also can see here is that we are not specifying any sizes on the AXI Lite interface itself for bit sizes, so it's a generic interface and can work with any bus size. And then we have here for specification data bits and number of frames. And there's a copy paste error. Sorry, the data D bits is wrong in here. Sorry, my mistake. Of course, we don't specify the number of data bits because it's coming from the bus itself. We just specify the number of frames and the depth of each frame. This is needed in AXI. We have certain meta information that are conveyed with the AXI stream itself. So like user bits, ID bits, and so on, they go into a separate FIFO data structure because here we need just 1 word per meta set. And the frame depth itself, this is for how many transactions you have in 1 burst operation. That's why we have then 2 generics specifying it in here. Yep, that's mainly then the interface for the FIFO that we have here. That's so far everything I wanted to talk about and show you as an introduction into our memory implementations. So let me go back 1 set here. Where is it? Yeah. To the agenda. So I have shown you starting with the on-chip memory abstraction layer to have a vendor independent, device family independent, whatever it is, independent implementation by using generic VHDL code, and in certain places using vendor specific code where the PoC-Library can switch between implementations. When we have such an implementation of a memory layer, we can build other higher level features on top of it. One was then having FIFOs implemented on top of simple dual port RAM, and based on FIFOs, we can have some FIFOs and buffers inside of our AXI4 network. This is my final conclusion for today, and I want to hand over to Anna for the final words.
Okay, thank you very much, Patrick. Okay, we have a look on the other slide at the end.
At the end?
QR codes, yes.
Yeah. I should have used this feature.
So, if you haven't done yet, please scan the first QR code to reach to the question platform. So please take the chance to ask our expert here live, so we can discuss that. So before we start with the Q&A, I want to talk a bit about other general points here from PLC2. The second QR code you can see is about our webinars on demand and the upcoming webinars in 2026. There will be the next webinar in the end of January about timing constraints. So if you are interested, please scan the code. And there you can also find the other parts of our PoC series. You can have a look on that. Then the third QR code you can see here is about our FPGA conference in Europe. It's in the next year in June or end of June, beginning of July. So please save the date here. There are also early bird tickets now available, and a new track will be there. This is about embedded AI. So we are already having 6 to 9 different tracks where you can choose your interest and courses, and this is a new embedded AI. So please have a look on that. It's a 3-day conference in Munich with lots of speeches and keynotes and exhibition hall and a special evening event at one day. So please have a look on that. And the 4th QR code is to our LinkedIn account. So stay up to date, and there will have different posts about PLC2 in general, our new courses, articles. So have a look on that. So now I think we can show you the Slido and have a look on your questions.
Why is it so it's not showing on my screen? Can you show your screen, then I can answer on your screen?
Okay,
Anna?
so maybe change now.
Have you encountered serious issues with in-out records in Vivado that requires separating? Yes. This is not Vivado problem. That's due to the language itself. So when you use an in-out, there is a second source created by the language in the background for every in-out port. And usually you have it also connected to another source where you drive signals inside of the record. So you are then facing a multiple sourced signal. So not a multiple driven signal, multiple sourced signal. Having multiple sources requires you to use resolved data types inside of your record. That's the first thing you need to do. So you're limited to unsigned, signed, standard logic vector, and standard logic data types inside of your record, which is usually for synthesis not a so big problem. Another one is that synthesizer a bit picky on figuring out ins and outs to see later in synthesis that a single bit is just used as ins and another bit is just used as outs. Another thing you need to adhere to is when you create the signal, you need to initialize it with a vector of z's, and this makes the handling overall quite complicated. And that's the main reason behind it. This technique in splitting records into two parts is called also the Aeroflex-Geisler method because they came up with it. So they are known for their Leon Spark implementation. And this was also one of the driving factors in VHDL 2019 to implement mode views. So there we have then an overlay on records defining for each individual element inside of the record the direction if it's an in or an out.
Okay. There comes another question directed to the code panel. Great inputs on splitting records. Can you list these as lint rules?
A list is lint rules. Okay. Reading
over here.
I'm not aware of any lint rules for this. So there are linting tools available, but I'm not aware if such a rule can be defined because it's usually not linting. This is an design technique, how to use it, and that's out of scope of linting. There's a question for which version of VHDL. So everything I have provided here is so far VHDL 2002 or 2008. Some of it would be even working with 93. Nowadays, all tools have at least 2008 support to a certain degree. That shouldn't be a problem. Except if you're referring to the mode views feature, this would be then 2019.
Okay, here's the question before he answered another. AM rather requesting you to define the rules.
I didn't get this.
Okay.
What is meant? You can also reach out to me by email, and then we can discuss this maybe then offline about the linting question. Yeah. In-out record pod generates warning.
Yeah,
So this
same.
Okay, that's the same.
Here we are reading.
One video part out of the videos.
Here's another.
The part 2 video on YouTube. This is still in cutting, right?
So yeah, I answered that
okay.
before. We had some technical difficulties, but it may be online in the next days. So I think there will be all parts.
And of course, this series here will also be
the fourth part also, yeah. And there's, I don't know, VHDL 2019 features.
Set as with select inside process.
Didn't work or?
I think that's a bit off topic from our implementation here. I'm not sure how this is referring to this. The VHDL 2019 feature with select. With select was not modified.
So
any other questions we have?
No more questions right now. So we will remain open the room a little bit more, I think, for the next 10 minutes. Yeah. And you can have any last minute questions if there are longer answers needed, or we are really, the time runs short, we will contact you afterwards via email. So please ask questions if you have some last minute ideas. And okay, before that, I will talk about our survey that will come up if the webinar ends. So please let us know what you think about the webinar and give us feedback. It's incredibly valuable to us and really important here for our upcoming webinars. So please give us your feedback on the survey at the end. And then
okay, then I have one last item.
Okay.
So this was part 4. And as I said, we will have new AXI Lite AXI Lite modules coming up early next year. That's the plan for the next release with the 4 modules I showed you: high resolution clock, OCRAM adapter, DRP adapter, and UART. So we will meet us then maybe here again at the next webinar, part 5, about these 4 modules. Okay, thank you very much and see you soon. Here's a
really short.
Solve an issue where record types with. I don't have an example to show it directly because we don't use this technique. As I said, there are certain problems with implementing in-outs. Or do you refer to a VHDL 2019 implementation? It would be too much to type it down to solve it compliant to VHDL 2008.
Okay. So then use the questions for the next 5 minutes if you have some ideas. So, and we hope you had a good time, and we see us in 2026, the latest, for the next webinar. So have a good time. Thank you for your time and have a great day, everyone.
Okay, bye.
Bye.